Hello, today we will learn about the recursive definitions. So, in the development of a mathematical theory, such as the theory of languages or the automata, the theorems and proofs may utilize only the definitions of the concepts of that theory. This requires precise definitions of both the objects of the domain and the operations. Now, a recursive definition of the set of natural numbers is constructed using the successor function s. So here in this example, suppose our basis, three things are important. What are the bases? What is the recursive step? And what is the closure? In recursive definitions, we need to focus on these three things. What are the bases? Suppose we say that here 0 belong to a natural number. Okay, natural numbers, in a set of natural number. So 0 belong. This is the basis. And the recursive step says that if n belong to set of the natural numbers, then s of n also belong to a set of natural number. Now this recursive function says that every time we need n plus plus, we need to increase one increment. Okay. Now the closure says that if n belongs to a set of natural numbers only if it is 0, or it can be obtained from 0 by a finite number of applications of the operation s. So the recursive step, there is the closure says that either the basic operation basis, what are the basis, or the application of the recursive step. Okay, so now here if you see, let's we produce the first few elements in n. So now how we can produce the first few elements in n? This is the basis. Okay, this is the basis 0. Now once we apply s, that is the recursive function, over the 0, then we got 1. 0 plus plus means 1 increment. Then this recursive function is again called and it is applied here recursively 2 times, so we got 2. Then this is the basis 0, and a recursive function is called once, twice, thrice, 3 times we called the recursive function, so we get the 3, and then so on. So in this way we can produce the first few elements in a set of natural numbers. So now we see recursively defined sets with infinitely many elements. So a recursive definition of set S has 3 parts. Basis, finite number of elements in designated as elements of S, recursive step, an operation or a collection of operation. This is very important. A recursive step can be an operation or a collection of operations is provided indicating how to form new elements. In the recursive step, this is the main thing, that how to form new elements of the set S from those that are known to belong to S. And in the closure is just a statement that tells us that the set S consists of only the elements specified in the basis and those generated by applying one or more operations specified in the recursive step. So in the closure, basically we need to tell about the basis and the recursive step. Okay, so we can get the required result. So recursive definitions plays an important role in the study of strings. The set of strings over a set of symbols. Now we see that if we have the set of strings over a set of symbols, like suppose here A and B are the symbols, okay, and this is a string that is not equal to the other string, like A, B, A, B, B is not equal to B, A, B, B. That here 4 times A and then B, B and the start also B. But we can get the length, any length of strings with the help of symbols A and B. Like let's suppose, see here, there is no symbol, okay, but it is a string, empty string. This is called empty string. And this is a string of length 1, only one A, one symbol. Similarly, the string of length 1, this is a string with length 2, having two symbols A, here A B, different symbols A B, but length is 2, only two symbols are there, and so on. Here we have a string of length 3, okay, but one symbol is A and two symbols are BB. Now here recursive definition of set S of all string consisting of the elements of the set A B, how we can get? Here basis is empty, we start from the empty, there is no a symbol here, empty string, zero length, okay. Then what is the recursive step? Recursive step is that if S belong to S, then SA belong to S and SB belong to S, where SA and SB are the concatenations of a string S with the symbol A and B respectively. So as in the closure, we know this thing that the bases are the empty string, that is S, and it can be obtained from empty string using finitely many operations of the recursive step. So how we can get the capital S or the set of all the strings? So see here, see, this is the basis, okay, this is the basis, we start from the basis. And in our recursive step, it is defined that either S is concatenated with A or the symbol B, okay, B. And here what is S? S in the basis, it is empty string, empty string. So the next one is A and B concatenated with the empty string, and we can write A and B. No need to write the empty string again. Now this recursive step is applied over this. So what we got? A concatenated by this A. This A is going to be concatenated by A. So we got AA. Then this A is concatenated by this B. So we got AB. Recursive step is applied on over both. Now this is the turn of this B, and the recursive step is again applied with here. So we got BA here, that is BA, and here when we apply B, so we got BB, okay. So this is the second iteration, and then so on. Similarly, this is the turn of AA. Now we apply the recursive step, this recursive step here, this recursive step again over this AB, okay. So what we will get? We will get A B. Like this is the A here and AB here. So this is the here, okay, and so on. In this way we get the recursive definition of the set S of all string consisting of the elements of the set A and B. So here there is another example. See this one also. The set of strings over a set of symbols. So here the basis is again the empty string, okay. We have the empty string, and recursive step says that AS then B belong to K or BSA belong to K. So here they are saying that in the basis, okay, K will have the empty string, then on the basis either we will have A empty string B, that is this one, or we will have B empty string A. This is the basis, the empty string is the basis, no need to write here. So we got these two. And in the second generation, what we do, we will apply this AB here on this recursive step. So what we will get? First A, then this AB, and then this B, okay. So what we will get? AABB, this one. Similarly, we will apply the same, this AB here, this AB here, we will apply on the second recursive step, like A, then but it says B, this is B na, and then this is AB and this is A. So we get B A B A, this one, okay, this one, and then so on. Like similarly, this we need to apply over it. How? Like we have BA, with the help of this recursive step we got A and B here, and with this recursive step we have BA, but here we have B and here we have A. So we got the next two, and so on. So in this way we get all these possible execution, the element generated in the third execution of the recursive step. So we will get in this way. Okay, and this is another example of recursive step. Like if we have here S is belong to this na, basis, and after the basis we have BA, or after here basis and before A and after that B, and here at the start basis and then at the end BA, and in these strings at the start B, then empty string, and then at the end A. So we will get this L set of strings that will follow the recursive steps. So we will get these strings, the set of strings. So is there any question or confusion? You can send me in the comments. Hope you like the video. Thank you.